Hi, welcome back. We're going to continue our discussion with the second derivative test. Now in part 1, we kind of mentioned in a really short way how we can tell if a function is concave down by looking at the derivatives. For example, here we have a maximum. We know that our first derivative is 0 and our second derivative is negative. It's less than 0. And if we have a relative minimum, our first derivative again is 0 and our second derivative is positive. Now there's a lot of reasons why the second derivative test that's not the best for us sometimes, mainly because the concavity, this has to be a smooth function all throughout. But it's very useful. It does have its applications, and we're going to talk a lot about them in this video. If we let f be a function such, and this is a more formal definition, if f is a function where the second derivative exists on an open interval, remember, no endpoints, we can't include endpoints, then we can say if the function has a first derivative of 0, so in other words we have a critical number, and the second derivative is positive, so we're saying that the function is concave up, we are saying if a function is concave up, at the very bottom, we have a relative minimum. If we have a critical number, again, the first derivative is 0, and then the function is concave down, we know that the function therefore is a relative maximum. And notice I always draw my picture out. We have a relative maximum. But what if we have a critical number, but our second derivative is also 0? Then what's happening here? Well, this is the official. We don't know, because if it's not concave up or concave down, we really don't know if it's a maximum or minimum. So for this, we must use the first derivative test. And this is one of the reasons why a lot of students don't really like the second derivative test, because in many cases we're going to use the first derivative test anyways. For example, here it says use the second derivative test, determine if possible, a great phrase, to find the relative extrema. So we're looking for the relative maximum and minimum of our function right here, of our polynomial function. Now, to be honest, for something like this, the first derivative test is a lot easier. I would not typically use the second derivative test here. However, they are asking me to use it, so I probably should. Now, where is second derivative test nice is when we have trig-licious functions, which we're going to talk about in just a few moments. And also, we have this example down here at the bottom, an application from the AP. Now, the reason why the first derivative test is sometimes much more useful, because we've already seen examples where this is a lot nicer to use. For example, in our in part 1, when we did the sign chart. See, the first derivative test tells us if we have relative max and min also. So we'll see. Let's take a look here. So our first step, of course, wrong way, zoom in. We need to find the critical numbers. To do that, we look at the first derivative, which is not too bad, negative 15x to the fourth plus 15x squared. I want to find out where that derivative is 0 or d and e. I don't need the z and e right here because it's polynomial, but I always have it just in case. So where is the first derivative equal to 0? I just set my function derivative equal to 0. I'm going to factor out a negative 15x squared, and we get x squared minus 1. And that's going to give us 0 and plus or minus 1. So now they are asking us to use the second derivative test, so I should use it. And our second derivative, negative 60x cubed plus 30x. So I need to first look at x equals 0. Therefore, the second derivative at 0 is 0. Now notice, this is our I don't know. Here, this fails. So therefore, this is telling me I have to use the first derivative test anyways. So doing my first derivative test, be very careful. I'm looking at the critical number at 0. So I want to find out what's happening at 0. Remember, this is my first derivative test, and how does it affect the function. Now, I don't want to pick numbers outside negative 1 and 1 because those are my other domain restrictions. So I'm going to pick a value between negative 1 and 1. I'll pick negative a half. Now, if you remember, this is multiplicity of 2 from pre-calc. We're going to use that in a second here. We'll explain that. So if I pick negative 1/2, well, the inside here is going to be positive. And even we take a look here, negative 1/2 squared becomes positive 1/4, times that by a negative 15, that becomes a negative. So the slope here is negative. It's going down. Well, what happens if we pick something like x equals positive 1/2? Well, again, the 1/2 squared plus minus 1. Oh, I'm sorry. 1/2 squared minus 1, that should be negative. Oh man, don't tell anybody I did that mistake. That should be positive right there. There we go. Two negatives make a positive. If we got 1/2 squared, negative 1/2 squared is 1/4 minus 1 is going to be negative. So we get two negatives there. So if we plug in the 1/2, same thing. We're going to get 1/2 squared minus 1, so that's going to be negative. And we also have this 1/4, 1/2 squared times negative 15, so we get negative again. And of course, two negatives make a positive. So if you notice on both sides, they're going up. Now, so what does that tell me? Is this a relative max or minimum? Well, to be a maximum, the slope has to go up and then go down. To be a minimum, the slope has to go down and then go back up. So because this time there's no sign change, the slope, it is neither. So this is neither. And the reason is because the first derivative of x does not change signs. Anyways, I also want to talk about what you guys learned in pre-cal a little bit. Because I had multiplicity of 2, if this side is positive, this side also has to be positive. Alright, so let's go ahead and now they are asking us to still use a second derivative. So we have two more possible points of two more critical numbers here, x equals 1. So if I find the second derivative at positive 1, let's go and do that. Because I'm using at 1. My second derivative here is negative 60 times 1 cubed plus 30 times 1. And if we notice, this is going to become negative. This is less than 0. So because that's less than 0, this is concave down. And I draw it out. Therefore, we have a relative maximum. So we know x equals 1 is a relative maximum. And that is because, and the quickest way to do it, the second derivative at 1 is less than 0. Let x be negative 1. Our second derivative at negative 1, again, plugging it in, negative 60 times negative 1 cubed plus 30 times negative 1. And this time it's going to be positive. Now, positive tells me it's concave up, so I draw something concave up. So therefore, I can say x equals negative 1 is a relative, that's a minimum, and that is because our second derivative at negative 1 is greater than 0. And that would be our answer. Remember, the biggest mistake people make is that, oh, it's greater than 0. It must be a relative maximum. But be careful, this is concavity, and that's why it's always good to draw that out. Well, use your hand. Concave up. There's my minimum. Concave down. There's my maximum. Anyways, the second derivative test is very nice for us if we don't have to use the first derivative test anyways. But again, on a problem like this, I would personally, if I give them the choice, I would just use the first derivative test. And you can see stuff like that in your homework tonight too, okay? Alright, so let's take a look at why we really like the second derivative test. So let's take a look over here. Use the second derivative test, if possible, to find the relative extreme of this trig function on 0 to pi. So we know we're going to need the critical numbers. This is where we really like the second derivative test. This is the only time I'd really choose to use it. Trig functions. I need my derivative, so that's going to become negative 2 sine x plus 2 cosine 2x. Don't forget, that's our chain rule. Now, I have to set this equal to 0. The problem is I can't solve it. So I am going to use one of my trig identities for this cosine of 2x. So this would become then 0 equals negative 2 sine of x plus 2. And I'm going to convert this to sine, and that just becomes 1 minus 2 sine squared of x. Simplifying this a little bit, we would get negative 2 sine of x plus 2 minus 4 sine squared of x. And I'm going to factor out a 2 and divide everything by negative 2. I'm going to factor everything up by negative 2 and divide everything to the 0 side. And that's going to give me 2 sine squared of x plus sine of x minus 1. And this I can factor. 2 sine of x minus 1, and I think this is going to be sine of x plus 1 equal to 0. So that's going to give me my critical numbers then. So if I solve this, ready? We would get, if I were to solve each one of these to 0, we would get sine of x equals a half, and sine of x equals negative 1. So where does sine of x equal 1/2? Well, that's just, what's that, pi over 6, and 5 pi over 6. And where does sine equal negative 1? That's 3 pi over 2. But my domain is from 0 to pi, so I don't have to worry about that one. That's out of the domain. And there's our critical numbers. Now, we're going to do the second derivative test. So I want to see if these are maximums or minimums. So I'm going to use my second derivative test. So my second derivative, this becomes negative 2 cosine of x. Be careful, chain rule, minus 4 sine 2x. And I plug each one of those in. Ready? At pi over 6, let's see if we can do this in our head. Negative 2. Well, what's the cosine of pi over 6? That's just root 3 over 2 minus 4. Be very careful. This becomes the sine of pi over 3. And because if I plug that in, that becomes pi over 3. So sine of pi over 3 is root 3 over 2. Now, I don't have to do too much. There's not really much math I have to do because I'm subtracting. So this is less than 0. So this is going to be, of course, concave down. We have a max. So we can say x equals pi over 6 is a relative max, and that is because the second derivative of pi over 6 is less than 0. And that's all we have to do. Plug in the 5 pi over 6. Let's see what happens. I get negative 2 times, that's a 6, weird looking 6, there we go. The cosine of 5 pi over 6 is negative root 3 over 2 minus 4. The sine, remember if I plug in the sine here, that becomes 5 pi over 3, which puts me in the fourth quadrant, so sine is negative, so it's getting another negative root 3 over 2. And these are positive, and I'm adding, because that's 2 negative make a positive, so this is going to be greater than 0. So therefore, this is going to be concave up. Notice I'm drawing it concave up. So we can say x equals 5 pi over 6 is a relative minimum. Be careful, it's a minimum value. Don't mess it up because you don't want to show work. Don't be lazy. That's where you lose points. And that is because the second derivative at 5 pi over 6 is greater than 0. And there's your answer. All right. Go to part 3, and we're going to take a look at an AP example. Again, now, the reason why we like the first derivative test is really nice for polynomial functions, because I can actually get it much quicker. If I were to do this one using, like I said, my sign charts, ready? Negative 1, 0, 1, f prime, and f. If I go back up here, if I know that these are both positive, positive, up, up, I know that I have negatives over here. So this is going down, and this is going down. So I have a relative max at 1 and a relative minimum at negative 1. Sign charts are easier for some polynomial functions, but trig functions can get really confusing in terms of their sign charts. So that is really nice where we use the second derivative test. But again, if they're going to ask you to use it, try to use it if you can. All right, so go back to part 3. We're going to take a look at an AP example here.